Welcome to my classroom. In this chemical process calculation course, we have been discussing about vapor liquid equilibria, wherein we are focusing on humidification operation. So in the previous lecture, we have defined you what is humidification, dehumidification, various applications of humidifications like liquid cooling, gas cooling, adiabatic humidification, dehumidification process such as solvent recovery, gas drying, refrigeration, air conditioning systems, or you have seen evaporative cooling and also water desalination plants. In all these places, we come across H and DH, that is humidification and dehumidification processes. Okay, so in this regard, we have defined various terminologies such as dry bulb temperature, dew point, what is humid volume, specific volume, right? We have seen what is humidity, absolute humidity, relative saturation, percentage saturation, and we have seen how to solve some numericals to determine if vapor pressure is known, how to determine the composition. All that have been discussed in the previous lecture. In the beginning of the last lecture itself, I had told we will be covering humidity chart in that, but due to time constraint, I had to stop at after 1 hour. So in this lecture, we are going to discuss about psychometric chart, how to construct a psychometric chart, and we will solve numericals using psychometric chart for various type of air conditioning system. Okay, so that will be the content for this particular lecture. We are going to discuss about humidification, and the contents of this lecture, the agenda for this lecture are: we will introduce what is wet bulb temperature, adiabatic saturation temperature, construction of a psychometric chart, and numericals using psychometric chart. So that we are going to cover in this lecture. Okay, and we have seen in the last lecture itself what is dew point temperature. It is the temperature at which condensation begins when the air is cooled at constant pressure system. In a constant pressure system, when the temperature of the air is reduced, so the first point at which the condensate is formed is dew point temperature, right? If a simple thermometer, you show it in the air, atmospheric temperature, if you measure, that is dry bulb temperature. Okay, the bulb of the thermometer, that is, we have mercury at the bottom, right? So what happens, where it absorbs heat, and due to the increase in heat, the thermometer level rises in the thermometer, right? So that way we measure it is scaled to temperature, we can measure the temperature, right? So what if we connect a wet wick is like a small cloth, a wet cloth which is saturated with water. What will happen? So the whatever is the temperature at which the air is coming in contact with the moisture, it will try to evaporate the water, right? So after that, when it is in equilibrium, so then the rest of the heat, or the rest of the temperature only will be reflected in the thermometer, right? So obviously, if you have a wet wick connected to a thermometer and a dry bulb thermometer, dry bulb thermometer will have a higher reading in the temperature, whereas this wet bulb will reflect some temperature less than the dry bulb temperature, because some of the heat is used to evaporate the water, right? So actually they will be in equilibrium. Okay, when the heat transfer that is taking place, that is to evaporate the water, and this bulb atmospheric air, the temperature will be coming in contact with each other. Okay, so actually evaporation needs some energy, right? Some heat is to be supplied to evaporate the water from the wet cloth that is connected to a bulb of the thermometer. Okay, so the wick, and therefore the thermometer bulb decreases in temperature below the dry bulb temperature, until the rate of heat transfer from the warmer air to the wick is just equal to the rate of heat transfer needed to provide the evaporation of water from the wick into the stream. So that equilibrium needs to be established. Okay, and this wet bulb thermometer is a function of humidity in the air, how much moisture is present in the air, what is the temperature at which the air is coming in contact with this wet bulb, and there are other parameters like what is the velocity with which air is coming in contact with the thermometer. Also the shape of the thermometer also contributes to this wet bulb temperature. Okay, so we have to take some precautions while measuring the wet bulb temperature. Why we have to measure it, I'll let you know. So first, while measuring this wet bulb temperature, what are the precautions that needs to be taken? So the wick must be completely wet. Okay, so that is should not be say some part is dry, some part is wet. So no such business. The wick should be completely saturated with water. I can say that that should be completely wet enough. Okay. So the second precaution is the velocity of the gas should be large enough, that is at least it should be around 5 meter per second, to ensure that the rate of heat flow by the radiation from warmer surrounding to the bulb is negligible in comparison to the rate of sensible heat flow by conduction and convection from the gas to the bulb. Okay, so this conduction convection we will learn in detail in heat transfer course in the next semester. And if any makeup liquid is applied to the bulb, that it should be at a wet bulb temperature. Okay, now we are defining what is wet bulb temperature. For example, if you are considering evaporation of water is taking place, okay, if the vapor pressure of the water is higher than the partial pressure of water vapor in the ambient air, what will happen? I repeat, if vapor pressure of the water is higher than the partial pressure of water vapor in the ambient air, evaporation will occur. So the latent heat of evaporation will be supplied by number one, surrounding airs and the water vapor itself. Okay, so if you consider a drop of water at the tip of a thin wire, and if the temperature of the water drop decreases with time, what will happen to the vapor pressure? The vapor pressure will decrease and it will cause a reduction in partial pressure driving force. So the temperature driving force for heat transfer from ambient air to the water will obviously increase, right? If sufficient time is allowed, a steady state of temperature will be attained by this water drop, and this temperature is called as wet bulb temperature. Okay, you can define the wet bulb temperature. It is the steady state temperature attained by a small amount of evaporating water in a manner such that the sensible heat transferred from the air to the liquid is equal to the latent heat required for the evaporation. I repeat, it is the steady state temperature attained by a small water drop. There is a small amount of evaporating water in a manner such that the sensible heat transferred from the air to the water is equal to the latent heat of evaporation required for the water to get evaporated. The temperature is called wet bulb temperature. We should know that wet bulb temperature will be always less than the dry bulb temperature, and at steady state we can say that adiabatic saturation temperature and wet bulb temperature are nearly equal for an air water system. For an air water system, we can say this wet bulb temperature is equal to adiabatic saturation temperature. Okay, and the difference between this dry bulb temperature and wet bulb temperature is called as wet bulb depression. What is wet bulb depression? It is the temperature difference between dry bulb temperature and wet bulb temperature. Okay, if you look at what is adiabatic saturation temperature, so we can say that it is the temperature at which the water by evaporating into air can bring the air to saturation at the same temperature adiabatically. There is no change in temperature, but by evaporation of the water we have saturation being attained. So that means in the 100% saturation line we will be getting this adiabatic saturation temperature. So we can call a device named as adiabatic saturator. It is a device which is used to measure the adiabatic saturation temperature experimentally. But practically speaking, this adiabatic saturation temperature cannot be measured easily. So for that purpose, we are going to make use of a experimental setup like a wet bulb thermometer with a wick. Okay. If you look at this adiabatic saturation setup, so you may have a isolated container where we will have water which is being kept at its wet bulb temperature. So the air is coming, unsaturated air comes, and when it is coming in contact with the water without change in temperature, much change, so it gets saturated, that is 100% saturated air is leaving the system. Okay, so we may be sending in some makeup liquid, but that liquid also should be in at the wet bulb temperature. Okay, so more or less we can say that adiabatic saturation temperature and wet bulb temperature are almost equal. Okay, and told a Sling psychrometer is an experimental device which is mainly used to measure the dry bulb temperature as well as the wet bulb temperature of the atmospheric air. Okay, which means what is the humidity present in it. All the calculation can be done once we measure wet bulb temperature and dry bulb temperature. We can make use of psychometric chart and determine all the thermodynamic parameters that is required for a air water system. Okay, so if you look at here, the adiabatic saturation process is not practically possible. So that way, to determine the absolute and relative humidity of the air, a more practical approach is to use a thermometer which has a bulb which is connected with a wick, and with wick is saturated with water by continuously supplying water to it. So it works in the fashion like kerosene lamps are being used, right? In the olden days, people are using kerosene lamp. You connect a cloth, and the cloth is connected to the oil kerosene, and the top is being fired. So we have a lamp be continuously burning to give us light, right? So in that similar fashion, this wet wick will be absorbing as water get evaporated into the air. The water is continuously being supplied to the wick, that thereby we are maintaining the wick wet, and we are going to measure the wet bulb thermometer. If you don't connect wet, whatever is the temperature measured, that temperature is called as dry bulb temperature, and the difference in dry bulb temperature and wet bulb temperature is called as wet bulb depression. Okay, next we are going to discuss about psychometric chart. Okay, so if you consider an air water system, that is particularly air, dry air plus water vapor is moist air, right? So if you consider a air water system, the properties can be determined using this psychometric chart, because from thermodynamic, all the thermodynamic properties and physical properties have been combined, and lot of experiments have been performed, and this psychometric chart is being drawn. Okay, so this will be serving as a valuable aid in visualizing the air conditioning processes such as heating, cooling, or humidification. Okay, so if you consider this is a schematic representation of a psychometric chart. So this is the schematic representation of a psychometric chart, where we have dry bulb temperature in the x-axis and specific humidity or absolute humidity in the y-axis, that is vertical axis, and horizontal axis we have dry bulb temperature and specific humidity. Okay, so here various terms such as specific volume, enthalpy, saturation, relative humidity, 100% saturation, dew point temperature, wet bulb temperature, all the definitions have been discussed in the previous lectures. Okay, so now we are going to see how we can make use of this psychometric chart. So how we can construct a psychometric chart first. For example, at this point, you have a 15 degrees Celsius and it is 100% saturation line. So this line is saturation line, that is relative humidity is 100%. Here we have any relative humidity. Okay, so 100% relative humidity, we have saturation line. So if it is 15 degrees centigrade, so we have dew point temperature also at the 15 degrees Celsius, right? And we are going to have a wet bulb temperature in this angle. Okay, so we will see how to construct a psychometric chart. Okay, so this is a typical psychometric chart. So you can see that 20, 25, 30, 35, 40, like this we have dry bulb temperature. Actually this particular chart is in old unit system, degree Fahrenheit and inches of mercury, like that. So still the representation is important. So we can see the dry bulb temperature is in x-axis. Okay, and this humidity ratio, or you can say as absolute humidity, is in y-axis. So you can see the unit of grams of water vapor per kg of dry air. So in this here it is grams of moisture per pounds of dry air. So we can have a different unit system. So you can see here wet bulb temperature is written in this class, that is 85 is wet bulb temperature, 80, 75, 70, 65, 60, 55, 50. So these are wet bulb temperature as written here. Okay, these lines. Okay, and we are having a line called as specific volume. So these black lines, so which are coming here, so this 1, 2, 3, 4, 5, 6, these 6 black lines represent specific volume. Okay, so I told you this is dry bulb temperature, this is specific enthalpy, specific humidity or absolute humidity. You have seen that this is 100% saturation line. So saturation is 100%. So this is 90% saturation line. You can say this 10% relative humidity, 20% relative humidity, 30%, 40%, 50%, 60, 70, 80, 90% relative humidity. So this is 100% relative humidity line, which means it is the saturation line. Okay. Apart from these parameters, you can see a scale for dew point. So you can see the scale being given here for dew point temperature. So dew point temperature is what, when you are cooling something, the temperature at the saturation, so corresponding to saturation, you can see 50 is wet bulb temperature, but the corresponding temperature in x-axis is going to be dew point temperature. Okay, then we have this enthalpy data here. So we can have enthalpy diagram. So enthalpy is H, right? Kilojoules per kg of dry air. So you can see the value varying from 10, 15, 20, 25, 30, 35, 40, 45, 50, 55, etc. Okay, so that way we have enthalpy can be determined for any point. So for any point, if I draw a line parallel to this thing, so we are going to get enthalpy data. So okay, so and other thing is specific volume. Yeah, this 14 specific volume is given, right? So this 14, 13.5, 13, 12.5, 14.5. So like that we are having lines for specific volume. So if you draw a line parallel to these lines, we are going to get the values for specific volume. Okay, specific volume means what? Meter cube per kg, right? Kg of dry air. Okay, reverse of it is going to be kg of dry air per meter cube. Okay, so we have specific volume here, and apart from that, you can see even some of the graphs will have vapor pressure also given. So the correspondingly we can get the value of vapor pressure also from the psychometric chart. Okay, and from any point we are having a temperature here. So here any point we are having a temperature. For example, this point is the dry bulb temperature is around 93 or 94, and if we are heating it from 95 to 110 degrees Celsius, so the process is heating. So when you are drawing a line from here to here, so initial and final, so what we are doing performing is sensible heating, because there is no change in humidity, there is no change in humidity, so only temperature change is there, sensible heating is being performed. Okay, but from the same temperature, if you are reducing the temperature from 93 to, say for example, 77, so what we are performing is sensible cooling. So that way we can get the parameter data. Say for, if I know initial conditions and what is the final condition, I can get the data corresponding to it, like enthalpy, enthalpy, what is specific volume, what is dew point temperature corresponding to this, what is absolute humidity. So all these parameters can be determined by marking these points, initial condition and final conditions. We can get the required parameters. Okay, same way if we are there is no change in temperature, however we are increasing the moisture content. As I said, this y-axis is your absolute humidity. Initially we are having a particular absolute humidity, okay, capital H. So if you are increasing it from initial value to some final value, so we are increasing the capital H value. So we have initial and final, so we can come to know what is the amount of moisture added to it, to the system. Okay, so that is humidification process. So we can without changing the temperature, we can still increase the humidification. We can increase the amount of water vapor present in the air. So that process is called humidification. And what would be the opposite of it? Without changing the temperature, if you are reducing the amount of absolute humidity, if you are decreasing, that is called as dehumidification process. That's called dehumidification process. Okay, so obviously from a psychometric chart, so all these parameters, there are various air conditioning processes. We can call it as air, for a air liquid system, pure liquid like water. If you consider dry air and moisture, so we can perform various operations and we can get the parameters corresponding to it, thermodynamic properties corresponding to it, using this psychometric chart. So for example, we can, as I earlier explained, sensible cooling can be done, sensible heating can be done. There is increase change in temperature, but there is no change in the absolute humidity, right? And in humidification and dehumidification, there is change in absolute humidity, but there is no change in the temperature of the system. Okay, then we can perform, if you are moving from this point to in this direction, in between sensible heating and humidification, we are going to have processes involving both. That is, we are going to heat as well as we are going to increase the humidity in the air. So such processes are, you can call it as heating and humidification is taking place. So both are taking place, and in the opposite direction, cooling and dehumidification is will be taking place. Okay, and similarly, when from this point, if we are moving from here this point to this point, what is actually happening? We are reducing the temperature and we are adding the moisture to it. Okay, so we are adding the moisture, so that way it is called evaporative cooling. Okay, this is called evaporative cooling, and opposite of it is going to be dehumidification process. Okay, so we are actually increasing the temperature and reducing the humidity in the air. That way it is called dehumidification system. Okay, so this, that is the, so for all these operations, if you have the psychometric chart and if you know only two parameters of initial and one parameter of the final, we can easily get the remaining parameters using the psychometric chart. So that way which is important for us. These are the motivation behind learning, why we should know about why to use the psychometric chart. Okay, so particularly for air conditioning processes, we are going to have sensible heating, sensible cooling, humidification, dehumidification, heating and humidification, cooling and dehumidification. Okay, but these things we are going to do, because particularly if to maintain any living space, as in the previous lecture I had told you, we have a comfort zone. We may be interested in just having a nice condition in the confined place. As I told, we cannot control the temperature of the universe. However, in the closed room, to make our life comfortable, we can have a comfort zone by using air conditioning system. Either we can increase the, because it is in winter, in cold countries, they want to remain warmer, right? Even in hill stations, so we want to remain warm, particularly during this winter season. Even in places like Warangal also we feel cold, right? So we may be using heater to increase the temperature, right? So we want to be warm during winter, and we want cold conditions during summer, right? So that way, this air conditioning, either we may be heating or cooling the air. Okay, we may be removing the moisture or adding the moisture to it. Okay, such processes are generally called as air conditioning processes, and air is commonly heated and humidified in the winter, as I told, and it is being cooled and dehumidified in the summer. Okay, and we can easily do the magnetic mass balance and energy balance for such systems. Okay, and if you look at the process like simple heating, what is to be done? When you have the air inlet, air is entering with a temperature and with a particular humidity. What we can do is, there will be a heating coil in the system, so that heat will be, the air will be heated. Okay, so and there won't be any change in the moisture in the, if you are considering, we are not heating the they are not changing the moisture content in the air. So in that case, this process, you can see that initially we are having a temperature T1, okay, 12 degrees Celsius, and it can be moving towards another temperature where we have 30 degrees Celsius, right? So this is simple cooling process. Actually, if it is, this is 2 to 1, it is heating process, and while the reverse of it is 1 to 2. That is, initially it is 30 degrees Celsius, we want to reduce the temperature to 12 degrees Celsius. So such process is called simple cooling, because it's only sensible cooling, because the humidity value, as I said, the humidity is y-axis value, humidity, there is no change in the value, so that is called simple cooling. Okay, and similarly during simple heating, the specific humidity remains constant, so we are going to have like this flat profile. And what happens to the relative humidity? As I told, the relative humidity terms are going to increase if we are moving towards left, because it is 100% saturation, 100% relative humidity. So as we move away from this line, we are going to have less relative humidity. That way, when you are heating and cooling, that is, when you are doing simple heating and cooling, that is, when you do sensible heating or sensible cooling, there will be change in relative humidity, but whereas the absolute humidity remains the same. Okay, and similarly there can be change in, we can do heating as well as we can do humidification also, right? So that way, if you look at this system, we are having a air, we have a heating coil, and we can have spray water to the air. What happens? We are increasing the moisture content present in the air, right? So in such system, there may be in this across the heating coil, there will be only, there is no humidification is done in this portion, right? So there is no change in absolute humidity omega 1 equal to omega 2, because both places have same y-axis value of omega 1 and 2. So that way we have humidity being constant, whereas the temperature T1 at the entrance and T2 is going to be different, because it is entering at 10 degrees Celsius, but it is leaving at 22 degrees Celsius after it getting heated by the heating coil, and then it is passing through a humidifier. It all takes place within a single system. Okay, it's not two different system. Continuously, this once it got heated, the hot air is getting humidified. So what will happen during humidification? We know the absolute humidity, the amount of water vapor per kg dry air is called humidity, absolute humidity. Obviously, when there are more vapor entering into the air, so we have increase in the absolute humidity. Okay, so that way from 2 to 3 we are going to have a different absolute humidity. Okay, so it is humidity gets increased. Okay, and what is happening when you are doing this one? As we are heating, obviously the relative humidity will decrease. Okay, so if you are leaving here, the relative humidity might have decreased, but by increasing it, what we have done is we are actually increasing the absolute humidity, relative humidity. Okay, so that is, if you consider this example, okay, so we have a air which is entering at a temperature of 10 degrees Celsius, and which has a relative humidity of 30 percentage, and we have a volume flow rate is like given, and we have, after this heat getting heated, we have 22 degrees Celsius. So 10 to 22, there is no change in change in absolute humidity, but this percentage relative humidity has changed. Okay, so from graph we can get this, what is the relative humidity. Okay, then in this humidifier, we are going to have further temperature of 25 degrees Celsius, and this relative humidity is increased to 60 percentage. So that way there is increase in relative humidity, whereas the temperature has increased to 25 degrees Celsius. Okay, and there are cases where we can do cooling with dehumidification. What happens to the specific humidity of air remains constant during this cooling process, which we have discussed earlier separately. But what happens to the relative humidity? It gets increased when you are cooling. Earlier case we are told when you are heating, the relative humidity, because this is higher, relative humidity is 100%. When you move away from this cross line, we are going to have less relative humidity, right? But when you are cooling, what will happen? The relative humidity will keep increasing, even though the absolute humidity remains constant. The relative humidity will keep increasing. Okay, what happens if the relative humidity reaches the undesirably high levels? It may be necessary to remove some of the moisture from the air, because if it is after saturation, what will happen? Condensation of vapor will take place, right? So once it reaches 100% saturation line, there we are going to have condensation. That means some humidity will decrease, right? Absolute humidity will decrease because it is saturated. Even by changing the temperature, we have made the air to get saturated with the whatever moisture it is having. Therefore, till that time, till it reaches this 100% saturation line, we have we had the same moisture, same specific humidity, we can say absolute humidity. But what happens after that? Since it got saturated, there will be decrease in the moisture content, that is there is decrease in the absolute humidity. That's why it goes to this point. Okay, so that's what is mentioned here. It may be necessary to remove some moisture from the air because it got saturated. So what is happening here? Obviously, so this process is dehumidification process. Okay, this requires cooling the air below its dew point. So what happens? We have to cool the air below the dew point temperature. So because this is the, for this condition, for this composition, this is the dew point. So below that we have to cool it to this temperature. Okay, that's what happens here. Okay, so some values are given here, you can see in this graph. And there is another term called evaporative cooling. I told you when you are doing evaporation, evaporative cooling can be performed. You can say that for a consider if we are in a desert where we have hot and dry climate, we can avoid the high cost of conventional cooling by using evaporative coolers, which is also known as swamp coolers. Okay, what happens here? As the water gets evaporated, the latent heat of vaporization is absorbed from the water body and the surrounding air. So as a result, what will happen? Both the water and the air are cooled during this process. So water in a porous jug left in open, breezy area, what happens? It cools as a result of evaporative cooling. Okay. So that's what happens even in winter. If you keep normal bottle with the outside and the fridge, you will observe that the normal bottle kept outside the fridge also becomes like a chill water, right? So that way evaporative cooling is taking place. Okay, this process is essentially identical to an adiabatic saturation process. Okay, so in evaporative cooling, what is happening? If you consider here, you can say hot dry air is entering. If you are just pouring, there is no heating coil is present here, you see, but still that the cooling is taking place. And if you are pouring liquid water, spraying liquid water, the hot dry air and liquid water, what happens? We are getting a cool and moist air. So that is called evaporative cooling. Okay, and there are mixing of air streams like adiabatic mixing. Okay, so when two air streams at state 1 and 2 are brought in, it's like fluid mechanics. You are seeing the mixing of two flow water, right? What will be the, there is change in cross section, and they are going to have volumetric flow rate being summation of volumetric flow rate in section 1 and volumetric flow rate in section 2. So that way we have seen such conditions, right? So here when you are mixing air the different with a different humidity, let me say it is having absolute humidity of omega 1 and absolute humidity of omega 2, which has an enthalpy of H1 and enthalpy of H2. Okay, so when they are mixed, it's obviously going to have a different um, absolute humidity omega 3, and the enthalpy corresponding to it is going to be H3. Okay, so that's what happens. So definitely this value is going to be between this and this. Okay, for example, let 1 represents the absolute humidity omega 1 and its corresponding enthalpy is H1, and here we are having a condition where omega 2 and H2. So the third point will be falling in between these two. So where it will fall, we can come to know through this psychometric chart. Okay, so we are going to get the value corresponding to y-axis is going to be absolute humidity omega 3, and the value corresponding to this enthalpy line is going to be H3, which is enthalpy of the mixed stream here. Okay, so that way these psychometric charts are useful to us. And there is one more thing which we are going to study in detail in next master answer course also. So wet cooling towers. So cooling towers are more essential unit operation in chemical industries or even in power plants. So even in thermal power plants, hydropower plants, there's a hot water that is coming here. So what we can do is the air will be at high temperature. We can use the air to cool the water. Okay, because the warm water or steam, condensed steam, will be at around a temperature of 80 or 90 degrees Celsius, right? So the condensed steam can be cooled, because we cannot send this warm water into the environment. Say for example, you have a lake. If you from your industry you send some flow rate of wastewater, which is at even though it may be pure water without any toxics, but still if the water is at 50 to 60 degrees Celsius, the lake water is mixed. When you are mixing this hot water into the lake, what happens to the aquatic life? Okay, they may get the plant may get suffocated, the plant may die, and there may be deficiency of oxygen, and the fishes living in it may die, right? So that way, so we should not let off the warm water into the environment. As a chemical engineer, we have this responsibility. We have to ensure eco-friendly operations being performed in the places that we are working. So the warm water needs to be cooled. So how we can cool this water? We can send air, atmospheric air will be coming in. So the warm water is sprayed. So the heat is carried away by the air. Okay, so the water gets cooled here. So that towers, it is carried out in towers like even 20 feet, 50 feet height towers, it is being done. We are going to study this cooling tower in detail in the next master answer course. Okay, so this wet cooling tower is an essentially a wet cooling tower. Okay, it is a semi-enclosed evaporative cooling. Why it is semi-enclosed? There is a opening for air to enter into the system. Okay, So we will see this, study this cooling towers in detail in the next master answer course. Okay. Say for example, we are having a data here. Okay. How to make use of the chart. So this is what we are going to do in this particular lecture. So we have a air water mixture. Two data will be given. For example, you have a temperature, dry bulb temperature, and relative humidity is given. So we should know to how to make use of this psychometric chart to determine parameters like humidity, percentage humidity, wet bulb temperature, dry bulb temperature, adiabatic saturation. All the parameters can be calculated in this one. So that's to further, first what we should do to solve problems of this type, we should able to know how to construct a psychometric chart. Okay, so this is a typical diagram for a psychometric chart. Okay, so you can see temperature is in degrees Celsius. You have humidity, absolute humidity, which is kg of water vapor per kg of dry air. So we have adiabatic saturation curves, and we have adiabatic saturation curve, and we have volume, specific volume, and we can have enthalpy mentioned here. Okay, we have humidity, humid volume. We have percentage humidity varying from 2 to 80%, 100%, 90%, and 100% percentage saturation. Right. So in the same temperature, we will have wet bulb temperature also. So these slanting lines, we are going to have wet bulb temperature. And we have enthalpy data scale is also there. Enthalpy can be taken. So different graph sheets will have find the data scales are given at different places. However, we should be careful in seeing what is the unit which is mentioned here. We have to use the appropriate units, and we have to convert it to required units also. Okay, so typically we are going to have so many parameters like dry bulb temperature, relative humidity line, wet bulb temperature, specific volume, wet bulb temperature, dew point temperature, what is the absolute humidity, what is saturation humidity, what is saturation line. So all that, what is the water vapor pressure. So all this can be used in a psychometric chart. Okay, so now we are going to discuss about how to construct a psychometric chart. So we should know each and line. So if you look at this line, it is very complex, right? So this is a complex line. So if you start learning what is each line representing one after another, it will help us to solve the numericals using this psychometric chart. So thoroughly we should know what are the various lines that represents what is the corresponding unit also. Okay. So if you look at here, we, as I said, in x-axis we are going to have dry bulb temperature. In y-axis, we are going to have humidity, which is kg of water vapor per kg of dry air. As I showed earlier, there are cases where they show in terms of grains per kg of dry air. Grain is also a unit which is used to mention how much grains of water vapor is present in per kg of dry air. Okay, so this is going to be absolute humidity line. Y-axis is absolute humidity, x-axis dry bulb temperature. That won't change for any different graphs also. Okay, and this line is this curved line. I am going to call it as curved line. This curved line is called as 100% saturation line. Understood? There are three areas we are focusing. One is dry bulb temperature in x-axis, humidity in the vertical y-axis, and in the curved line we have 100% saturation line. Okay, so whenever they ask what is the value at the current saturation, we should go to this 100% line. That is a 100% relative humidity is the saturation line. Okay, so we have in x-axis dry bulb temperature. So what is dry bulb temperature? It is the temperature measured by ordinary thermometer when the bulb of the thermometer where the mercury is there, it is being dry. Okay, so typically it is in horizontal axis. Okay, so then we have seen what is wet bulb temperature, right? When you have a wet wick connected to the bottom bulb of the thermometer, so its wet bulb temperature is going to be always less than the dry bulb temperature. So okay, so we have wet bulb temperature being drawn in this cross angle. Okay, so you can say this inclined lines in brown color. I hope you don't have color blindness. You are able to see this brown color. So you can see this colored line is wet bulb temperature. You can see the reading mentioned here 30, 40, 50. You can see this value corresponding to dry bulb temperature of 40. We have 30 is the value. So that way it is connected. So 50 wet bulb temperature is 40. Okay, so that line is wet bulb temperature line. Okay, so what is wet bulb temperature? It is a air temperature which is measured by a thermometer having a wet sensing bulb. Okay, wet sensing bulb is wet wick mostly, right? So there is a equipment which is device which is available in the market. There is a like rotating equipment. So you will hold it in your hand and rotate 3 to 4 times. So that we will measure both the dry bulb temperature and wet bulb temperature. Then you can refer to the chart, or you can have a digital things also. These two input is given, corresponding value can be displayed. Okay. So that way, here we are having wet bulb temperature line. This earlier slide I showed you brown line. Here it is. These blue lines represent wet bulb temperature. Okay. As I said, this curved line is called saturation line. That is 100% saturation line. So if it is line next to it is going to be less saturated. So 100% saturation line. So then you are going to have a 90% saturation, 80% saturation, and 70% saturation. Okay, so these are called saturation lines. Okay, so first what we have seen, dry bulb temperature, absolute humidity, wet bulb temperature. Now we are seeing saturation lines. Okay, so these are saturation lines, and then we are having the saturation lines are also called as relative humidity. Okay, so when I say relative humidity is 100%, 80%, 60%, 40%, 30%, 20%, 10%, like that. Okay, so that is relative humidity line or percentage saturation. Okay, and then we have specific volume lines. Okay, what is specific volume? It is the reverse of mass density, right? Kg per meter cube. So you can say this is the volume occupied by per kg of dry air. Okay, so that is meter cube per kg of dry air, which is specific volume. So you are going to have the specific volume line. So the data may be either in the line, the scale may be given at the below the dew point dry bulb temperature, or it may be given like this in this side. Okay, so but when we want to, how to get a value in between, so if something is there in between, we have to draw a line parallel to this. So I might have not have drawn a parallel line, but this whatever is the value, those lines will be parallel to each other. Okay, so for example, specific volume this and this will, all four lines should be parallelly drawn. Okay, and then we have another line, because remember we should not confuse these two lines, because with one angle we are going to have specific volume line, and with another angle we are going to have enthalpy scale also in the same fashion. Okay, so if you are considering it to be ideal gases, the lines of constant enthalpy, and these lines are parallel to wet bulb temperature. Okay, we have already seen in that brown lines I have shown you that it is representing wet bulb temperature, but in the same lines of wet bulb temperature, if you are extending to the scale given outside the saturation line, that is the value for enthalpy. I know the unit of enthalpy, it will be given in kilojoules or kilocalories per kg of dry air. Per kg of dry air, how much kilocalories, or sometimes it may be given in kilojoules. Okay, so we should take appropriate units. Okay, then so thus we have seen so different points. So here we are going to get dry bulb temperature. Okay, so from this same dry bulb temperature, corresponding, when if you without changing the humidity you keep saturating it, when the percentage saturation increases, at 100% saturation what we get is condensate of the first. Once it is humidity is not changed, but we have reduced the temperature such that the air is saturated with water vapor, then what will happen? Condensation will begin, right? So that is the dew point temperature. The corresponding temperature at 100% saturation is our dew point temperature, which we can take from the same x-axis scale. Okay, so the temperature corresponding to 100% saturation line for any particular humidity is called dew point temperature. Okay, so which will be taken from the 100% saturation line and moving towards x-axis. Okay, so another thing is, by extension from the given point, if you go towards left hand side in the x-axis and get the x-axis value, so what we get is dew point temperature. Similarly, from the given point, any given point in the same dry bulb temperature, you keep, without changing the temperature, you keep increasing, you keep humidifying it. So what is the maximum humidification possible? It is at 100% saturation line, and the corresponding y-axis will be the final specific humidity, or absolute humidity. So absolute humidity value, that is your saturation humidity. What is the saturation humidity corresponding? This is actual humidity, but what is the same temperature? What would be the maximum possible water vapor that can be present in the air? So you can extend the line to this y-axis, where it meets the 100% saturation line. Corresponding value in the y-axis gives us the saturation humidity. Okay, so the saturation humidity can be obtained by extending the line parallel to y-axis and getting the corresponding x-axis value. We get saturation humidity value. Okay, so that way we are having another psychometric chart given here. You can see the dry bulb temperature is in degrees Celsius. We have y-axis value 0.0, 0.005, 0.10. Humidity ratio of water, humidity, which is grams of water per grams of dry air, which means kilograms of water per kilograms of dry air. So this is one, and we are having these red lines varying from 0%, 10%, 20%, 30%, 40%, 50% relative humidity, and it goes on up to 100% humidity. This is percentage relative humidity line, RH, relative humidity or percentage saturation. So what we have here is 100% saturation line. This curved outermost curved line is our 100% saturation line. Okay, and we have seen that these blue lines are called wet bulb temperature. You can see that wet blue lines is varying like this. So these lines are called wet bulb temperature lines. Okay, and similarly, as I said, for lines parallel to wet bulb temperature are enthalpy saturation lines. So we have enthalpy lines here, right? So we can see this value is given in joules per gram of dry air, which is equivalent to kilojoules per kilogram of dry air. So we can say that it is 20 kilojoule per kg of dry air, 40, 60, 80, 90, 100. So this is enthalpy value can be taken. And if you look at carefully here, it is given here is specific volume in meter cube per kg of dry air. Okay, so that way we have these green lines, light green lines. Color is immaterial, even if it is black and white, we should be able to identify it. These lines parallel to each other are the lines corresponding to specific volume. So if I am looking at this point, what is the specific volume? I have to keep a scale here and move it across here parallel to this line, and I have to mark the line and get a value between this and this. This is 0.85, this is this. So by using any method, you can get the value in between value. Okay, you can make the use of the ratio method. What is the total length, what is this length, and what is this length? Okay, so mostly it is our wise decision to take. Okay, if it is exactly at the mid this green line and this green line, if it is off the distance from each one, so we can say that it is going to be the value of 0.85. This is 0.80, 0.90, so it is going to be 0.875 in between. So it is, so values in between less than 0.875 can be taken here. 0.875 to 0.9 will be coming across this line. Okay, so that way between two parallel lines, whatever is your point, you have to take judiciously, cautiously, we have to take the value. Okay, so this is an example of this partial saturation and humidity chart. So this is a diagram where we usually have hot water entering from the any process, chemical process, from steam turbines or whatever it is. Hot water is coming, it will be sprayed here. So atmospheric air will be here at this point. It is open condition. So the air will be entering. So the air will get absorb the heat as well as it get vaporized, or air will be leaving here. Okay, so what we get is cold water coming from it. The whatever moisture it is trying to carry will be eliminated using drift eliminators. Okay, so this type of tower cool, this type of building, whenever you come across in any power plant or any chemical industry, so these are cooling towers. Okay, so we have seen that air conditioning in case of water cooling, humidification, and particularly drying operations also, this thing is to be done. Air and vapor are coming into contact with each other. Okay, so thus air stream or stream of hot flue gases pick up the moisture from a solid substance is called drying operation. Okay, even in drying operation in cement industries, food industries, pharmaceutical industries, we may use hot air, which will be taking away the moisture in the from the surface of the solids, right? So that drying operation, again you will be learning in detail in master answer 2 in your third year or fourth year. Okay, So from this psychometric chart, whatever we have seen, so now we know how to construct a psychometric chart. So once you are able to construct a psychometric chart, we can properties such as dry bulb temperature, wet bulb temperature, dew point, specific humidity, relative humidity, specific enthalpy, specific volume. If any two parameter is known from this chart, psychometric chart, we can able to get the rest of the parameters without using any equation and all. We can simply mark the points in the graph, and if you know the procedure how to take the readings, we will be able to get the values. Okay, so that is the remaining values can be determined. So as I said, so your x-axis is going to be dry bulb temperature, horizontal line, vertical line is going to be specific humidity or absolute humidity, and a cross line is going to be wet bulb temperature. Okay, and we are going the line parallel to wet bulb temperature, we are going to have enthalpy also, right? And we have seen specific volume lines also. We know how to get dew point. Okay, so that way we are going to make use of the psychometric charts extensively for air conditioning applications, various air conditioning applications. I have explained the theory part, concepts of what is humidification alone, what is sensible heating, what is sensible cooling, what is humidification, what is dehumidification, what is evaporative cooling, right? So what is chemical humidification, right? So that way for different processes, if two data is given at one system and it is changed to another point, we should able to get the points corresponding to it, and we can able to determine even further parameters, various parameters. Okay, so from that way, this psychometric chart, we should not be afraid of looking at the graph. You will see the name, everything will be mentioned here. We have to take time patiently, we have to observe what is the data given, what is the unit in which the data is given, also important. It's not sufficient you just take the data and assume some unit and try to carry forward. Okay, so we should look at the what is the graph, because we are going to make use of different chart, right? Depending upon that, you have to see which graph I am using, what is the data given in it. Okay, it is better you use the one chart you make use for all your course, particularly if you have a psychometric chart stored in your laptop, make use of that chart only, because you will be thorough with what are the units corresponding to it. Okay, so this is again humidity chart, temperature which is humidity. So this is 100% humidity line. We have adiabatic saturation line will be given here. Okay, so we can get that one also. Adiabatic saturation point will be at the dew point temperature. Okay, so the 100% saturation line, this S and R. Okay, so all will be corresponding to the adiabatic saturation lines. Okay, so we have just recall how to determine this molar humidity or molal humidity. It is the for air water system. It is the number of moles of water vapor per number of moles of dry air, which can be given as partial pressure of A by partial pressure of B. A and B are A is water and B is dry air. So we have PA by P minus PA. These formulas we are going to make use in the numericals we are going to solve. That's why I am just recalling. These things have been discussed in detail in the previous lecture, in which all the terms are defined. Okay, so here I am giving you equations to use directly. Okay, and if you say what is molar saturation humidity, at saturation we know that partial pressure is equal to vapor pressure. I told you the superscripts of S are not PA naught or PAS, or even capital P subscript V, we can represent the vapor pressure. Okay, so that way we can substitute for this, and we can still get what is molar saturation humidity. Okay, if you know the partial pressure. And we can see what is relative humidity or relative saturation. It is the partial pressure of A by vapor pressure. So actual partial pressure exerted by the vapor by vapor pressure of the liquid at the same liquid temperature T. Okay, and it is in percentage, so we are multiplying by percentage. Okay, what is percentage humidity or percentage saturation? So we have seen the ratio Na by Nb, and divided by Na by Nb at saturation gives us percentage humidity. Okay, this we have defined explained in the previous lecture, please go through it. So we have Pa by Pb by Pas by Pbs, we get percentage humidity. And we should even able to make use of the steam tables. Okay, so for example, if percentage relative humidity is known, saturation pressure at the given temperature can be taken from the steam table. So for given relative humidity, what is the saturation pressure can be taken from the steam table. So you should able to get that one. If RH is given, we should able to get this saturation pressure. Okay, so if saturation pressure is known, what is the vapor pressure? We have the formula relative humidity is equal to PV by PS, right? PV is the vapor pressure where PS is the saturation pressure. Okay, and another term is vapor density. What is vapor density? So it is the ratio of absolute humidity divided by specific volume. So see, you have defined what is mass density. We should get kg per meter cube, right? So similar to that, what is the vapor density? The density of vapor is vapor density. So how we can get with the whatever data that is available from the graph, psychometric chart is, if you know absolute humidity, what is that? It is kg of vapor per kg of dry air. And we are going to get the from graph what is specific volume. What is the unit of specific volume? Meter cube per kg of dry air. So kg of dry air, kg of dry air gets cancelled. So what we are going to have is kg of vapor per meter cube. So kg of vapor per meter cube is the mass density. So that is the density of the vapor, which is termed as vapor density. So we should, if it is asked to determine the vapor density, we have to divide absolute humidity by specific volume. Both values can be taken from graph. Okay, so you can divide them to get the unit kg per meter cube. Okay, so that formula also we are going to make use of. Similarly, what is the mass flow rate? How to get the mass flow rate? Because always it will be asked how much heat is added. How much heat is added? We know enthalpy data can be obtained from the chart, right? H1, H2, there are 2 points. For example, initially we have a condition at temperature T1, condition 1, and it is increased, dry bulb temperature is increased to T2. So there is sensible heating taking place. So from the chart we are going to get what is the enthalpy of the initial condition and what is the enthalpy corresponding to final conditions, right? As I said, the unit of enthalpy is going to be kilojoule per kg of dry air. So we know how much heat is associated with this. So how much heat is added when increasing the temperature from T1 to T2 is can be obtained by mcp delta T, right? Similar to that, m into change in enthalpy. So m dot is going to be mass flow rate. You should know what is the mass flow rate. So how much kg per minute it is flowing, it is being heated, right? So how much mass, what is the mass of dry air? We should know how much mass of the dry air is being circulated, and we should know how much heat is being added, right? So for that, enthalpy data H1 and H2 we will get from psychometric chart. How to get m dot value? It won't be given, m dot won't be given directly, maybe volume will be given. So this much volume of air is being entering into the system. So volume with the unit of meter cube is given means, if that's why it's starting I have written, if volume in meter cube is given, m dot can be determined by volume divided by specific volume. Volume is meter cube, specific volume is meter cube per kg. So if it is given volumetric flow rate is given, meter cube per second or meter cube per minute or meter cube per hour is given, we are going to get continuous flow rate kg per second or minute or hour we are going to get with respect to time. Okay, so what is specific volume? As I said, from the graph we can get the specific volume, which has the unit of meter cube per kg. So when you divide volume by specific volume, meter cube gets cancelled. So if minute is here, we are going to get kg per minute. So that way this m dot value will be obtained by dividing the given volume by specific volume. So that such type of problem also we are going to do. How much heat is added to the system or how much heat is removed from the system. So if it is sensible cooling, this H1, H2 is going to be different. But this is going to be 1, this is going to be 2. Okay, we have to take care of sign conventions. Okay, and there is a factor in refrigeration, they call it like bypass factor, because we are having what happening, we are having a cooling coil, warm air is entering each, where it is ideal conditions, each warm air molecule is supposed to reach the surface of the cooling material and then get cooled, then leave it. But there is a probability some fraction of air may be away from traveling, escaping through the regular path, and they may not get cooled, so they may be escaping, so there may be bypassing taking place. Okay, so that is a condition of non-ideal condition. So there may be some bypass, so that factor is defined, how much fraction is getting bypassed without getting cooled. So that factor is called bypass factor. So you can see here, some of the air flowing through the coil impinges on the water tubes or the fins and is cooled to the adiabatic saturation temperature. Remaining air passes through unchanged. Okay, so that factor is called bypass factor. This percentage of the air that passes through the coil unchanged is called bypass factor. Percentage of air that passes through the coil unchanged is called bypass factor. As I said, that they don't get cooled. Warm air, they goes warm air. So how much percentage is leaving like that is called as bypass factor. Okay, so bypass factor, how to determine? There is a formula. Okay, we can see that adiabatic temperature is there. So the inability of the coil to cool or heat the air to its temperature is indicated by a factor called bypass factor. What does it mean? It had initially had the potential to reduce the temperature to one level. Okay, but actually it is not reaching the target level. So for example, here TD1 is your dry bulb temperature of the air entering the system, and TD2 is the dry bulb temperature of the air leaving the system. We are having another point called adiabatic dew point temperature. Okay, so if you look at this, if these three parameters are known, you can determine what is the bypass factor. What is the bypass factor? It is the percentage of the air which goes without getting cooled in the system. Okay, so you can redefine this bypass factor in another way. It is the ratio of the air which is unaffected by the coil to the total quantity of air passing over the coil. Okay, what is the total quantity of air passing? Is the denominator. How much of the air did not get cooled or did not get heated in the system? That is that one. So it is the numerator. So numerator divided by denominator, we get bypass factor, and which can be given by the range. So okay, TD2 minus ADP. Okay, that is the fraction which did not, it is supposed to get cooled, but it did not get cooled. Okay, so that way TD2 minus adiabatic temperature, adiabatic dew point temperature, divided by total, that is TD1 to ADP is a total one. Okay, so this is called as bypass factor. So some numericals we can even determine the bypass factor. Okay, we should know how much it is not actually getting cooled. How much fraction of the air is not getting cooled can be determined using this bypass factor. And there is another factor called as sensible heat factor. Sensible heat factor is, say for example, in this type of evaporative cooling or evaporative heating. Okay, sorry, in case of this kind of processes where you don't have parallel line and horizontal line. Parallel line represents, parallel to x-axis, it represents sensible heating or sensible cooling. Vertical line operations represents either it is humidification this way or reverse dehumidification. Okay, so the process moving from here to here or here to here can be termed as two processes. It can be equated to these two processes: horizontal one, sensible heating plus humidification, right? If it is moving from B to A, or if it is moving from A to B, we can say it is dehumidification plus sensible cooling. So that way this can be related. So we can have enthalpy corresponding to our H1. A is initial, let me say A to B, it is moving, we are cooling. What you can say, H1 is the enthalpy of the initial point, H2 is the enthalpy of the final point, and we have H3 which is sensible corresponding to this line. So we can sensible line. Okay, so horizontal line is sensible, so you can imaginary line you can draw. So the point corresponding to it, what is the H3 value? So this H3 minus H2 divided by H1 minus H2 is called as sensible heat factor. Okay, so we should, from the graph we have to, initially you will be getting H1 H2 without any problem, but finally we should not forget, if sensible heat factor is given, so we have to draw a triangle diagram here, and the point corresponding to this and what is the corresponding H3 value we have to determine from the graph. Okay, as I said, you have to draw this line and get the H3 value from the graph. Okay, and there is another term called as heat extraction or heat addition capacity. What is the heat capacity of the cooling coil? So already we have seen how to determine m dot value, which is the ratio of given volume, initial volume by initial specific volume corresponding to initial value. We should not get confused which specific volume to use, because initial point, final point, but volume is given initial, right? So divide by the initial specific volume. So initial point is given two parameter. It may be dry bulb temperature and humidity, or dry bulb temperature and wet bulb temperature, or dry bulb temperature and relative humidity. So whatever is given, so that corresponding initial conditions, specific volume has to be taken. That's why I written at one represents initial or condition, initial condition. We always write 1 to 2, the process operation is being carried out. Okay, so capacity of the coil is m dot into h1 minus h2 gives us the heat extraction or addition capacity. Okay, heat addition capacity or heat extraction capacity. Okay, a higher value minus finer smaller value. Okay, and this m dot is, you will be having the unit of kg per air per minute, right? So I told you it is, we can obtain it by volume divided by specific volume, meter cube per minute by meter cube per kg. We are going to get kg per minute, which is mass flow rate. So in that, if question comes, how much of water is removed or added, how much water is added or removed can be determined by knowing what is the initial humidity, what is the final humidity. So humidity difference, we know initial humidity minus final humidity. As I told, small h is used for enthalpy, capital H is used for absolute humidity. So initial absolute humidity minus final absolute humidity, higher value minus lower value, into whatever is the mass flow rate of the air. Okay, so we have m dot is the kg air. Okay, kg of air per minute. So we will get what is the amount of water removed. In terms in refrigeration, particularly when you are buying AC, so there will be asking question, what is your room size, how much ton AC is required, 1 ton AC or 1.5 ton AC we have to buy. So what is the ton? Actually, what is the ton? That ton is not our 1000 kg. Okay, so we should know what is the ton of registration, which is coming under this air moisture system. Okay, so if you call what is tons of refrigeration, a ton of refrigeration, which is also called as refrigeration ton, it is a unit of power used in some countries to describe the how, what is the capacity, what is the heat extraction capacity of a refrigeration and air conditioning equipment. Okay, so we may have it, either it is for refrigeration or air conditioning equipments. We have to describe the what is the heat extraction capacity, what is the capacity to extract the heat. Okay, so that is called as tons of refrigeration. Okay, or sometimes it is called as refrigeration ton. It is defined as the rate of heat transfer that results in the freezing or melting of 1 short ton of pure ice at 0 degree Celsius in 24 hours. Okay, so that way it is defined. So just for unit conversion purpose, we may use, so 211 kilojoules per minute is equivalent to 1 ton of refrigeration. So that unit conversion is important, because sometimes even you calculate what is the heat capacity, all that, so you may have to convert it into TR. Okay, don't get reminded of the political leaders, someone. So TR refers to tons of refrigeration, which is equivalent to 211 kilojoules per minute. Okay, so the definition is there, the rate of heat transfer that results in the freezing or melting of 1 short ton of pure ice at 0 degree Celsius in 24 hours. Okay, so once we are thorough with these concepts, it is easier for us to proceed to solve the numericals. So please go through these formulas, or what are the formulas which we are going to make use of it, and be thorough with it. Okay, so even if you don't remember the formulas, as I said, if you are clear about what is the corresponding unit, by dividing, multiplying, taking ratios, we can get the required values. Okay, in this lecture we have discussed about wet bulb temperature, what is adiabatic saturation temperature, how to measure wet bulb temperature, right? How, what is the construction of psychometric chart have been covered. Even though I had told that we will be able to solve numericals, so we have already crossed 1 hour, so I have to end this lecture here. So in the next lecture we will see how to make use of psychometric chart to solve the numericals. Actually, whatever concept that is covered and whatever equations are given, you will able to start solving the numericals using psychometric chart. Okay, so still I will solve some numericals in the next lecture. So in this lecture we have covered what is wet bulb temperature, adiabatic saturation temperature, how to construct a psychometric chart, each line, what is that x-axis, what is y-axis, what are the different data that can be derived from the psychometric chart have been explained in detail in this lecture. I hope you have understood all the concepts. If you have any doubts, please contact me. Thank you so much for joining my classroom.